Hello there, and welcome to Life Beyond Seen, where the pace settles, the lights dim a little, and science takes on the gentler shape of something you can listen to while your body unwinds. Tonight we're moving far from the familiar world of sunlit coastlines and surface waves. We're drifting downward, past where most ocean life decides it has no business going, into a region where pressure climbs, sunlight disappears, and the usual rules of living don't seem to matter much anymore. Hidden in that darkness are cold seeps, places where methane and hydrogen sulfide leak from the seafloor in slow, steady streams. These leaks look nothing like rivers at the surface, yet they behave a bit like them, forming channels that move through the sediment and spread across the bottom. They aren't warm, they don't sparkle, and they certainly don't smell pleasant. They carry chemicals that would harm almost anything that evolved in ordinary conditions, including us. And somehow, despite all of that, entire communities thrive right beside these toxic flows. It's a strange corner of the planet, quiet, dim, and hostile in some ways, but also busy with life that learned to make these chemicals not just tolerable but essential. While we spend our days breathing oxygen and strolling around in comfortable pressure, the creatures out there use methane the way we use food, and rely on bacteria that can transform substances that would send us fleeing. There's a lot to explore, and before we get too deep into the biology or the chemistry, it's worth asking something simple. Where are you listening from tonight? Are you somewhere quiet, maybe settling down for the evening, or are you listening during a break, catching your breath and easing into a calmer moment? Whatever the time is where you are, thank you for being here. And if you find this relaxing or interesting or simply helpful as background for a quieter night, it would mean a lot if you liked the video or subscribed. It helps this space reach others who might also want a slower way to learn about the world. Settling into this story doesn't require knowing anything about oceanography or geology. You don't need to picture complicated diagrams or memorize numbers. You only need to imagine descending through the ocean, where the last patches of light fade and the surroundings take on the muted look of deep water. At first, the world feels empty. That's the common expectation. Most people assume the deep sea is a deserted stretch of mud and rock. But after a while, something begins to shift. In the beam of a submersible's light, you start to see faint movements in the sediment. Little flickers of life, currents carrying particles, slopes dotted with shapes that resemble fields rather than deserts. You hear descriptions from scientists about faint shimmer-like distortions drifting above certain patches of seafloor. That shimmer signals the presence of seepage, cold and chemical-rich, escaping from underground stores and forming a boundary between one layer of water and the next. These fluids aren't cold in the sense of being icy. They're cold only when compared to the vents that often steal the spotlight in documentaries. Hydrothermal vents shoot out water hot enough to cook an egg in seconds. Cold seeps are different. They aren't dramatic fountains or boiling geysers. They release their chemicals quietly. Slow seepage, steady flow, sometimes seeping from cracks, sometimes pooling in smooth depressions known as brine lakes. These lakes look remarkably like small bodies of water sitting inside larger water, which is an odd sight to imagine. The liquid is so dense with salt or gas that it forms a separate layer, with its own surface and its own currents. Submersibles can even leave faint ripples on these surfaces as they move through, like skipping across a pond hidden 3,000 meters beneath the waves. The first researchers to encounter these areas didn't expect them to be lively. The chemicals that leak out, especially hydrogen sulfide, are toxic to most surface life. The pressure is high, the temperature is low, there's no sunlight. Photosynthesis, the foundation of surface ecosystems, isn't an option. So the expectation was a kind of quiet wasteland with maybe a few microbes clinging to what little they could find. Instead, explorers found thick mats of bacteria, fields of mussels, clusters of clams, and tall gatherings of tube worms that look almost like underwater forests of pale, upright stems. Not only was life present, it was thriving. It was building entire communities with structure, competition, cooperation, and long-term stability. The question that follows is simple. How? How does life manage in conditions that should be impossible for most organisms? How do animals breathe when the chemicals around them are harmful? And what enables them to gather in such dense numbers, forming ecosystems that rival the productivity of some shallow water environments? The answer begins not with the animals, but with the bacteria living inside them or coated across the sediment. These bacteria use methane and hydrogen sulfide as energy sources. They handle processes that most life forms want nothing to do with. They convert substances into usable energy the way plants convert sunlight. The animals then form partnerships with these bacteria, hosting them in their tissues in exchange for nutrients. It's a kind of biological teamwork that looks efficient rather than elegant, direct, practical, and well suited to an environment where efficiency matters more than appearances. Before going further into these relationships, it helps to picture the conditions at the seafloor. Imagine a place with no day-night cycle. The only changes come from shifting currents or the occasional disturbance when sediment collapses or a new crack opens. The water feels dense. Sound travels well, but there isn't much movement. The cold seep areas contrast with the surrounding mud plain, not because they glow or swirl with colour, but because their inhabitants gather in clusters that stand out against the background. Tube worms hug the seep edges. Mussels form thick groups, like patches of cobblestones. Clams bury just beneath the sediment. Small crustaceans scurry between them, taking advantage of the structures created by the larger animals. Fish appear occasionally, drawn by the promise of food in an otherwise sparse environment. All of this forms a system that humans didn't expect to find. When the first research teams documented these communities, they were struck by how active everything looked. Not chaotic, but purposeful. The bacteria grew in mats that resembled patches of felt. The animals arranged themselves in ways that seemed to maximize access to the seep fluids. The surrounding terrain looked like a landscape shaped by slow flows that carved small channels, similar to the way rain shapes soil on land. Only here the rain was methane-rich water emerging from the earth. In many ways, this environment pushes us to reconsider basic ideas about habitability. We tend to define a livable environment based on our own needs. Oxygen, sunlight, mild temperatures, reasonable pressure. Cold seeps ignore all of that. They support life that doesn't share our requirements, and that alone makes them worth exploring. Not because they offer a fantasy of alien worlds or dramatic scenes, but because they demonstrate how flexible life can be. The conditions that seem favourable or unfavourable to us don't dictate what is possible for organisms shaped by different pressures and histories. Life does not need to resemble us to be successful. It only needs a reliable way to gather energy and reproduce. The more scientists study cold seeps, the more they realise that these environments play a meaningful role in global processes. They influence the movement of methane, a potent greenhouse gas. They shape the seafloor over long stretches of time, reinforcing or weakening sediment layers depending on the rate of seepage. They create stable habitats that last for centuries, sometimes millennia, and then eventually become inactive, forcing their residents to move or adapt to dwindling resources. These transitions aren't sudden collapses. They happen gradually as the seep slows, and the chemical supply decreases. The communities adjust slowly, thinning out or shifting to nearby active areas. In a sense, the ecosystem breathes on geological timescales, expanding and contracting as the planet's deep plumbing changes course. There's a continuity to this that feels steady rather than dramatic. Cold seeps don't erupt, they don't explode, they don't transform overnight. The pace matches the calm monotony of the deep ocean, and yet, the persistence of life around them adds an undercurrent of activity. Every bacterial reaction, every tube worm's growth, every mussel colony's expansion is slow but consistent. Over the course of decades, these small processes build significant structures and support large numbers of animals. It's a kind of patience that doesn't attract much attention until someone shines a light on it. Thinking about all of this while settling into a quiet moment can create a sense of steady curiosity. The kind that doesn't overwhelm or rush, but keeps nudging you forward into the next part of the story. Cold seeps aren't dramatic at first glance, but they open a door to understanding a version of life shaped by different constraints. They give insight into how organisms can find structure in places that don't seem to offer much. And they remind us that the world has layers we rarely consider during everyday life. As the seep communities come into clearer focus, the pieces begin to fit together in a way that encourages following the thread a little further, seeing what else lives there, how the systems grow and what roles these places play in the broader picture of Earth's story. Down in the quiet regions where sunlight never reaches, the surroundings develop a kind of steady sameness that almost tricks you into believing nothing unusual could possibly happen there. The water remains cold, the pressure keeps everything compacted, and the landscape looks like a wide sweep of mud that could stretch on without interruption. But as you move across that terrain, the appearance shifts in subtle ways. The seafloor develops faint patterns that don't match the uniform plane you might expect. You notice narrow channels etched into the sediment, small ridges, and slightly rippled areas that hint at flow even though no obvious current is moving across them. These markings come from the seep fluids rising through cracks, spreading outward and forming invisible pathways that resemble rivers more than anything else, even though they don't behave like rivers at the surface. They don't sparkle, they don't rush, and they don't carry the kind of water you'd touch willingly. These flows transport methane, hydrogen sulfide, and other chemicals that most animals would instinctively avoid. Yet here, those chemicals form the backbone of the community. The first impression of these toxic rivers is usually one of surprise because they don't look hostile. There aren't clouds of dark smoke or violent bursts of gas. Instead, the fluid seeps out smoothly and quietly, blending with the seawater but still maintaining enough difference in density to form soft boundaries. If you were to watch from inside a submersible, the seep might appear as a slight wavering, a distortion the way heat bends air above a road. That shimmering effect comes from the chemical-laden fluid rising and mixing into the surrounding water at a relaxed pace. It doesn't burst through, it slides, meanders, and continues its course with a consistency that doesn't draw attention unless you look closely. That understated quality is part of why these areas remained unknown for so long. They don't announce themselves with dramatic changes, but they reshape everything around them. To understand why the flows carry such a harmful mix, it helps to think about what sits beneath the seabed. Organic matter buried under layers of sediment slowly breaks down over thousands and millions of years. The deeper it goes, the more pressure it experiences, and the more its chemical components shift. Microbes trapped underground continue working under those high-pressure, low-oxygen conditions. They digest the organic material in ways that produce methane and hydrogen sulfide as byproducts. These gases accumulate in pockets and are pushed upward over time through cracks and fissures. By the time they reach the seafloor, they've built up concentrations strong enough to make the area immediately around them completely unsuitable for standard oxygen-based organisms. The strange part is that life still appears here, not incidentally but intentionally, in dense presence rather than scattered traces. The rivers of toxic fluid move like very slow weather systems, shaping the sediment by softening some areas and hardening others. Hydrogen sulfide in particular has a way of reacting with minerals in the sediment, forming crusts or cement-like patches that make the terrain uneven. Some places become firm enough to support structures that wouldn't stand on ordinary mud. Other places remain so soft that anything resting there sinks slightly, leaving impressions that show where larger animals once gathered. The mixture of hardened and softened areas creates a patchwork landscape, each section signalling different chemical concentrations to the creatures that depend on these flows. As the seep fluid spreads, it changes the chemistry of the water just above the sea floor. Oxygen is quickly used up where the chemical reactions occur, creating thin layers where conditions flip from toxic to tolerable and back again in just a few centimetres. For most animals, this kind of instability would be a clear warning to move away. But in these dark regions, it works almost like a signal. Where the shimmering layers appear, life finds nourishment. The flows bring chemicals that bacteria can use the way plants use sunlight, and where the bacteria flourish, the larger organisms gather. The rivers may be poisonous to outsiders, but to the residents of the seep they are dependable sources of energy, flowing in slow, continuous patterns that support entire networks of life. The absence of light plays a larger role than it might seem at first. Without sunlight, there's no difference between day and night. There are no shadows or passing clouds. The animals don't orient their activities around cycles of brightness or darkness. Instead, they respond to chemical gradients. The shape of the river becomes the cue. More than anything visual, creatures sense where concentrations rise or fall. Small invertebrates follow these trails like paths. Even larger animals such as fish spend time near the edges of the seep, adjusting their position depending on how the fluids shift. It's a world tuned more to chemistry than to light, and the animals behave accordingly. Hydrogen sulfide is one of the strongest components shaping life here. For surface animals, including humans, it interrupts respiration almost immediately. It binds to molecules that our bodies use to process oxygen, preventing the normal flow of energy. Down here, though, bacteria have evolved entirely different pathways that not only tolerate hydrogen sulfide but rely on it. They oxidize it, meaning they burn it the way we burn calories, and in doing so they create the energy that supports both themselves and their hosts. Methane works in a similar way. Specialized microbes convert it into usable energy, forming another layer in the food web. Where these bacteria cluster, the toxic rivers act like feeding grounds. The rivers don't stay neatly organized. They branch, split, and sometimes fade into the surrounding water before reappearing in new places. The seafloor shifts slowly over time, and the flow paths respond to these changes. As cracks open or close, the fluids reroute, sometimes forming new channels and letting old ones diminish. Organisms adapt to these shifts. Tube worms, unable to move once anchored, rely on long bodies that reach toward the seep fluids even when the source shifts slightly. Mussels form dense patches in locations where the seepage remains stable for long periods. If the flow dwindles, the mussel beds thin out and nearby animals move on. Nothing happens quickly in these zones, but everything does eventually change as the seep adjusts its output. These rivers carve deeper impressions in some parts of the sediment where the chemical reactions cause the mud to collapse slightly. The edges of these depressions often attract more bacteria because the seep fluid pools there, staying longer and giving the microbes sustained access to the chemicals. Small animals gather around these pools, searching for bacterial mats to graze on. Sometimes the depressions become so pronounced that they resemble small basins, each holding a mixture of seawater and seep fluid dense enough to discourage mixing. The visual effect is subtle but recognisable under artificial light. The surface may look like a darker patch or a slightly reflective film. One of the more striking features of these toxic rivers is that they operate independently of the surrounding environment. While surface rivers respond to rain, weather and gravity, the seep rivers respond to pressure differences within the earth. Their flow continues whether storms hit the surface or not. They remain steady even during seasonal cycles. The deep ocean feels none of the temperature shift that affect upper layers. Everything is calm, and because of that calmness, the progression of the seep becomes easier to track. Scientists can observe how the flow changes over years, how new outlets form, and how old ones shut down without the noise of fluctuating conditions interfering. Despite their stability, the seep rivers don't last forever. Over long timescales, the reservoir beneath them can drain or shift. As the supply of methane or hydrogen sulfide decreases, the flow weakens. The bacterial mats begin to thin. The tube worms produce fewer offspring. Mussel beds become patchy. It's not a sudden event. The decline moves at a pace matching the environment itself. slow, steady and subtle. Animals drift to nearby active seeps, following the new sources of chemicals. The old seep eventually quiets, leaving behind mineral deposits that record the history of the flow. These deposits form layered structures that scientists can analyse long after the seep becomes inactive. Each layer contains clues about how strong the flow was, what chemicals were present, and what organisms once lived there. While the seeps are active, though, the rivers of toxic fluid shape everything in their path. They determine where life can root itself. They dictate which animals gather in which areas. They influence the formation of microbial communities. They even impact the geological structure of the region by binding sediment or softening it. In that way, the rivers behave almost like architects, sculpting the landscape through consistent contact rather than force. The creatures that live near these flows respond to the slow rhythms of the seep, rather than to any external clock. They aren't following tides or sun cycles. They follow gradients, chemical cues, and the presence of bacteria. That makes their behaviour predictable in some ways. They remain near the boundaries where the toxic rivers meet normal seawater, because those boundaries provide the best balance of conditions. Too close to the source and the chemicals become overwhelming. Too far away and the bacteria cannot thrive. The sweet spot lies along the margins, where conditions shift just enough to allow both bacterial growth and animal survival. Those margins guide the arrangement of the community. Looking at these rivers through a submersible window, you wouldn't see anything dramatic. There's no movement like a flowing stream on land. Everything stays quiet. But the chemical interactions are constant. Methane bubbles rise in slow trails from the sediment. Hydrogen sulfide dissolves into the water and interacts with surrounding minerals. Bacteria anchor themselves to surfaces where the flow remains steady. Even without motion, the process stays active at every second. It's a silent, unhurried kind of dynamism. Understanding this quiet, chemical-driven world sets the stage for observing the organisms that depend on it. The toxic rivers reveal the blueprint of how the ecosystem is arranged, showing why certain creatures gather in specific locations and what allows them to function where others cannot. The more time one spends watching the subtle shimmer and the shifting layers, the clearer it becomes that the toxic mixture isn't simply a byproduct of geological processes. It's the foundation of an entire way of living, built on reactions that proceed steadily as long as the seep continues to supply the chemicals. The rivers shape the landscape, direct the biology, and maintain the continuous flow of energy that keeps everything active in a place that would otherwise be quiet and empty. When people first began sending cameras and instruments into the deeper parts of the ocean, the expectation was fairly modest. The goal was often to map the seafloor, measure temperature, and document whatever marine life happened to pass through the lights of the equipment. There wasn't much anticipation of finding anything unusual beyond the occasional fish or drifting invertebrate. The deep sea was treated less like a frontier and more like empty space, a kind of underwater desert that covered most of the planet yet remained assumedly uneventful. That idea held on for a long time. Even as technology improved, the assumption stayed fixed in place. The deep ocean was supposed to be quiet, uniform, and largely barren. Then, gradually, instruments became more capable, the dives extended deeper, and the first hints of something unexpected began to appear. Early deep-sea explorations didn't focus on looking for cold seeps. No one had reason to imagine they existed. The ocean floor was thought to be stable. Substances like methane and hydrogen sulfide weren't considered part of the biological picture down there. The teams that launched the earliest expeditions were more interested in geological formations, mid-ocean ridges, and the surprising presence of life around hydrothermal vents once those were discovered. It took time for anyone to notice that there were other types of fluid emissions, quieter and colder, that didn't resemble the spectacular chimneys of black smokers, but still created distinct environments. Cold seeps revealed themselves slowly, and only to observers patient enough to examine the subtle clues on the seafloor. One of the key shifts that allowed these discoveries came with the development of submersibles that humans could ride in. Remote cameras were helpful, but human eyes inside a pressurized sphere provided a different level of detail. Researchers could look out a window and notice textures and patterns that machines might overlook. They could linger in one place, investigating anything faintly unusual. When these submersibles first reached depths where cold seeps were present, the explorers didn't yet know what they were seeing. They noticed patches of unusual sediment, slight discolorations, or shimmering layers hovering just above the bottom. These observations weren't dramatic, but they didn't match the standard idea of the deep sea floor, and that difference encouraged more investigation. The teams who ventured down were trained to look for anything that stood out. At the time, their discoveries involved more guesswork than certainty. Some of the shimmering layers were dismissed as distortions from the submersible's lights. Some of the unusual sediment patches were assumed to be artifacts of the camera. Only after repeated dives, consistent recordings, and the appearance of similar anomalies across different locations did the patterns start to take shape. Something on the seafloor was leaking fluid. Whatever it was, it didn't match the temperature spikes associated with hydrothermal vents. It emerged at ambient deep-sea temperatures. That observation opened a door to a new category of underwater phenomena that hadn't been considered before. The first explorers saw the seep communities before anyone knew exactly what they represented. Thick clusters of mussels and clams appeared where the shimmering layers hovered. Tube worms extended from the sediment in places where the fluid seeped most consistently. Dense mats of bacteria formed on surfaces that received steady chemical flows. These organisms were not scattered sparsely. They formed structured, sizable communities. The explorers weren't expecting that. It contradicted their understanding of deep-sea life. The deep was supposed to lack energy sources. Without sunlight, no photosynthesis could occur. Without photosynthesis, most food webs should collapse. Yet here were thriving ecosystems, anchored not to sunlight, but to something bubbling upward from the earth. When these scenes were first shown on monitors aboard research vessels, the reactions ranged from confusion to excitement. No one could explain why there were dense gatherings of life in areas without light and without heat. Early hypotheses suggested that the animals must be feeding on organic material drifting down from the surface. That idea dissolved quickly once researchers examined the sheer density of the communities. The amount of food needed to support them exceeded anything that could plausibly fall from above. Something else was powering this ecosystem. The explorers had uncovered habitats dependent on chemical energy rather than sunlight. Collecting samples became the next step. Submersible arms gathered sediment cores, scooped up bacterial mats, and carefully lifted clams and mussels from their beds. The idea was to bring everything back to the surface for analysis. The researchers expected confusion, but what they found went beyond that. The animals' tissues contained bacteria living inside them. These bacteria weren't invaders or infections. They were symbiotic partners, essential for survival. The animals didn't rely on digestion in the typical sense. Instead, they housed microbes that converted methane or hydrogen sulfide into energy. This discovery reshaped how scientists understood deep-sea life. It was the first clear evidence that chemical energy could support complex communities in cold, dark environments. The explorers who made these discoveries often described the scenes as startling, not because they were dramatic, but because they contradicted everything they had been taught. In marine biology, energy flow seemed clear. Sunlight supported photosynthesis, which supported nearly every food chain on the planet. Hydrothermal vents broke that rule with heat-driven chemistry, but cold seeps broke it more quietly. Here, life thrived under conditions that looked unremarkable at first glance. The explorers had to adjust their interpretations and realize that the lack of heat did not mean a lack of energy. The fuel simply came from different molecules. These first encounters required not just observation, but a shift in thinking. The explorers had to stop assuming that life required certain familiar ingredients. They had to study organisms that survived in low oxygen conditions, that partnered with bacteria in sophisticated ways, and that built entire communities without relying on the sun. The discovery redefined the boundaries of what counted as a habitable environment. It expanded the frame of reference well beyond Earth's surface and drew connections to possibilities on other worlds, although the researchers didn't focus on that directly. Their aim was simple: understand what was happening in front of them, not far beyond it. As exploration continued, different regions revealed their own variations of the seep environment. Some seeps produced strong flows rich in methane. Others offered more hydrogen sulfide. Some generated brine pools so dense that submersibles could create small ripples on their surfaces. Each new environment carried the same core principle: fluid emerging from below supporting a community above. The explorers documented these systems methodically, building maps that showed how widespread the phenomenon was. They found seeps in the Gulf of Mexico, off the coast of Oregon, near Japan, along continental margins, and in several unexpected corners of the ocean. The more they looked, the more they realized these hidden springs weren't rare. They were simply overlooked. The deep ocean's camouflage, darkness, pressure, uniform appearance, hid them well. Only after repeated dives did the explorers learn how to recognize the signs quickly. The shimmering distortions, the clumps of mussels, the unusual sediment consistency, the presence of tube worms indicating a stable chemical source. With experience, they grew better at navigating towards seep zones and documenting their extent. Each new site provided variations that added nuance to the overall picture. Understanding these early discoveries helps explain why cold seeps feel so intriguing now. The explorers did not stumble upon them expecting to rewrite sections of marine ecology. They found them by paying attention to the small deviations that signalled something out of the ordinary. Their discoveries were built on patience, careful observation, and willingness to challenge outdated assumptions. They spent long hours inside cramped submersibles or monitoring remotely operated vehicles as they crawled across the sea floor. Visibility was limited. Maneuvering was slow. Communication with the surface was controlled. Despite these constraints, the explorers traced the faint signs of seepage until they uncovered the communities that depended on those flows. Even now, the accounts from those early missions reflect a mixture of restraint and enthusiasm. The explorers knew they were seeing something biologically significant, but they also understood that their interpretations required rigorous testing. They didn't rush to conclusions. They collected samples, took measurements, and let the evidence shape the understanding. Their work formed the foundation for everything known today about seep ecosystems, from microbial processes to geological interactions. The detail and precision of their observations allow present-day researchers to track changes, understand long-term cycles, and explore how these systems influence the broader ocean. The early explorers also faced technical challenges. The deep ocean demands equipment capable of withstanding extreme pressure. Any malfunction could end a dive prematurely or risk losing samples. Cameras often struggled in low-light conditions, and early sensors lacked the sensitivity to detect slight chemical gradients. It took years of engineering refinement for instruments to become accurate enough to record the nuances of seep environments. But with each improvement, the explorers gained more insight. They detected methane plumes rising through the water column. They identified the minerals forming around seep sites. They measured the flow rates that determined how quickly the chemical rivers spread across the sea floor. All of this revealed that the seeps were not isolated curiosities. They were part of a larger pattern shaped by Earth's geology. The explorers realized that these springs reflected deep processes, shifting sediments, rising fluids, and long-term cycles of organic decay. The seeps offered a window into the connection between biological and geological systems, a connection that became more apparent with every dive. As time went on, the teams developed a clearer idea of how to study seep communities. They created sampling strategies to avoid disturbing the delicate chemical gradients. They improved mapping techniques to record the layout of seep zones accurately. They established long-term monitoring sites to track changes over the years. The explorers who began this work didn't just find cold seeps. They built the framework for understanding them. They recognized that these hidden springs were more than geological features. They were ecosystems shaped by slow, steady chemical processes that supported dense and stable forms of life. Their discoveries paved the way for continued exploration, encouraging new generations of researchers to investigate the connections between chemistry, biology, and geology in the deep ocean. The first explorers revealed that the deep wasn't barren. It simply required the right perspective to notice the subtle signs of life. The hidden springs they found became a reminder that the planet still holds environments waiting quietly for someone to observe them closely enough to understand how they work. And as those signs became clearer, the story of cold seeps expanded, connecting the early glimpses to the broader understanding of how these ecosystems support themselves and what lives within them. In the dim regions where seep fluids drift upward from the sediment, the surroundings appear deceptively simple at first. The light from a submersible reveals only muted colours, soft shadows, and the slow movement of water that barely hints at any sort of activity. But once your eyes adjust to the scale of the place, the life that gathers there begins to stand out in quiet but unmistakable ways. What seemed like ordinary lumps of sediment become clusters of mussels. What looked like scattered sticks reveal themselves as tall, pale tube worms anchored in the mud. The faint coating on the seafloor transforms into dense blankets of bacteria. Everything sits in a dark world where nothing seems designed for conventional survival, yet these organisms not only persist but flourish in steady numbers. The first impression most people have when they view this environment is disbelief, not because the creatures appear strange in dramatic ways, but because their presence contradicts familiar assumptions. The conditions around them lack light, warmth, and the oxygen-rich water that supports most marine life. Instead, there are chemicals that would cause immediate harm to typical fish, crustaceans, or humans. Yet the animals here behave as if they have found a suitable home, one that provides stability, nourishment, and long-term resources. The fact that they do well in a setting defined by toxicity challenges the idea that harshness must correlate with scarcity. In this environment, the steady release of methane and hydrogen sulfide creates a dependable foundation for life. Looking closely at the animals reveals how thoroughly they have adapted to their surroundings. Take the tube worms, for example. At first glance, they look like simple, upright tubes rising from the sediment. Their pale bodies stand several centimetres to several metres tall, depending on the species and age of the colony. They do not have mouths, stomachs, or digestive tracts. Instead, they rely entirely on bacteria living inside their tissues. These bacteria process hydrogen sulfide, converting it into energy the tube worms can use. Without the bacteria, the tube worms could not survive. Without the tube worms, the bacteria would not have a stable home with access to the chemicals they need. The relationship is tightly integrated, allowing both partners to thrive in conditions that would be impossible for them individually. Mussels and clams living near cold seeps follow a similar pattern. Their tissues contain symbiotic bacteria capable of metabolizing the seep chemicals. The animals themselves help regulate the flow of chemicals through their bodies, ensuring their bacterial partners receive a constant supply. In return, the bacteria provide nutrients that support the animal's growth and reproduction. This type of relationship requires remarkable internal control, since the chemicals involved must be managed carefully to avoid harming the host. Over time, these animals have developed structures and behaviours that allow them to position themselves precisely along the chemical gradients, where the balance works best. Too close to the seep source and the concentration becomes overwhelming. Too far and the bacteria starve. Their ability to find and maintain the right location demonstrates an awareness of chemical cues far more refined than anything most familiar marine animals possess. The communities built by these organisms appear stable because they rely on continuous chemical supply rather than on fluctuating food sources drifting from the surface. In many ocean environments, the food web depends on seasonally variable plankton blooms. In cold seeps, the energy source remains steady as long as the seep is active. This allows animals to form dense clusters, with muscles crowding together so tightly that their shells interlock. Clams bury themselves in patterns that maximize access to seep fluids. Tube worms grow in groups that form structures resembling small, upright forests. The density of these organisms reflects the unusual abundance created by chemical energy. Even though the environment looks barren from a distance, the underlying biochemical reactions deliver enough energy to support complex life. Beyond the larger, easily observed animals, the seep environment hosts countless smaller organisms that contribute just as much to the structure of the community. Isopods, amphipods, polychaete worms, and small crustaceans move through the bacteria-coated sediment and across the surfaces of mussel beds. Some feed directly on bacterial mats. Others rely on the organic material produced by the larger animals. A few species specialize in scavenging or in consuming the mucus or waste produced by tube worms. Their presence adds layers to the food web, showing that the ecosystem supports not just primary consumers, but also secondary and tertiary ones. The idea that such trophic levels could exist without sunlight challenges older models of marine ecology and broadens the understanding of how energy can circulate through deep-sea systems. Fish appear occasionally around seep sites, especially species adapted to low-light conditions. They do not rely on the chemicals directly, but they take advantage of the concentration of smaller animals and potential prey around the seeps. Some species may pass through regularly during foraging cycles, while others settle nearby long-term. Their behaviour suggests an awareness of the opportunities created by the seep environment. Even species not specifically adapted to the toxic chemicals can use seep communities as feeding grounds, provided they navigate the chemical gradients carefully enough to avoid harm. The bacteria, although invisible to the naked eye, form the true foundation of the community. Their ability to process methane and hydrogen sulfide determines how much energy is available for the rest of the ecosystem. They grow on surfaces exposed to seep fluid, forming layers that can reach several centimetres thick. These mats become food for grazing animals and provide shelter for smaller organisms. The bacteria also stabilise sediment through their growth patterns, helping shape the physical structure of the seep area. Their presence transforms the seafloor into a patchwork of biochemical activity rather than a barren mud plain. The diversity of organisms at cold seeps varies from region to region, but the overall pattern remains consistent. Wherever the chemicals rise, life forms that specialise in chemical processing gather. Their presence creates further opportunities for additional species, which in turn attract predators or scavengers from outside the seep environment. This layering effect leads to communities that resemble miniature ecosystems despite the absence of light. It's a pattern repeated across oceans, whether the seep sits in the Gulf of Mexico, the Mediterranean, the Pacific margins, or the slopes of the Atlantic. Each site hosts variations adapted to local conditions, but all follow the same underlying model. Bacteria harness chemical energy. Animals partner with the bacteria. The larger community forms around that relationship. One of the striking aspects of seep life is how calm everything looks. There are no fast movements, no signs of urgency. The organisms grow slowly, react slowly, and operate on timescales that differ from those of shallow water species. But slow does not mean simple. Many of these creatures manage complex biochemical processes that would overwhelm typical marine animals. Their tolerance for hydrogen sulfide, for instance, requires specialized adaptations at the cellular level. Their tissues must prevent the toxic molecules from interfering with respiration while simultaneously delivering them to the symbiotic bacteria. This type of regulation demonstrates a high degree of physiological specialization. The lifespans of many seep organisms reflect their slow growth. Some tubeworm species live for centuries. Their growth rates are so gradual that measurable changes require long-term observation. The symbiotic bacteria within them remain stable throughout their lives, maintaining the relationship through careful balancing of chemical exchange. Mussels and clams can live decades. their colonies expanding slowly as conditions allow. Even the microbial populations show persistence, renewing themselves steadily rather than cycling rapidly the way surface bacteria often do. The long-term stability of these relationships shows how well the organisms are tuned to their environment, maintaining equilibrium as long as the seep continues to supply the necessary chemicals. Despite this equilibrium, the creatures remain sensitive to subtle changes. A slight decrease in chemical flow can alter the distribution of bacteria, which then affects the animals relying on them. Tube worms may grow more slowly. Mussel beds may thin in certain areas while expanding in others. Clams may shift their positions as they follow chemical cues. The stability of the community depends on continuous seepage, but within that steady framework exists a dynamic adjustment process that allows the ecosystem to respond to gradual shifts without collapsing. The resilience shown by these creatures provides insight into the flexibility of life. They survive in conditions that seem entirely unsuitable from a surface perspective. They rely on energy sources that would harm or kill most animals. Yet their adaptations allow them to convert what appears toxic into something sustaining. This reveals that habitability is not defined solely by conditions comfortable for humans or familiar animals. Life can anchor itself to environments that seem incompatible with biological processes and still form complex, stable systems. The creatures living around cold seeps demonstrate that survival depends on matching physiology to opportunity rather than following universal templates. While sunlight supports surface ecosystems, chemical reactions fill the same role in deep-sea seeps. The animals dependent on these reactions are not exceptions. They're examples of life adjusting to available energy sources. Their existence suggests that wherever a steady form of energy emerges, whether from light, heat, or chemical seepage, life has the potential to develop around it. Observing these creatures gradually builds a more complete understanding of the seep environment. Each organism contributes a small piece to the overall picture. The tube worms provide structure. The mussels offer dense clusters of habitat. The clams regulate chemical access. The microbes supply the energy. Smaller animals connect these layers through feeding, movement, and scavenging. Together they form a system that appears improbable from the surface, but becomes logical when viewed within its chemical context. Spending time studying these creatures highlights a core idea that applies throughout the deep ocean. Unfamiliar conditions do not equate to impossibility. The animals around cold seeps demonstrate that life adapts not by resisting its environment, but by integrating with it. They don't avoid the chemicals, they incorporate them into their biology. They don't seek oxygen-rich water, they exist comfortably without it. They don't require sunlight, they rely on microorganisms that use molecular energy instead. This understanding builds naturally toward exploring how deeper interactions shape the community. The adaptations of individual organisms reveal only part of the story. The full picture emerges when examining how these creatures work together, how bacteria influence animal behavior, how chemical gradients control growth patterns, and how the entire system expands or contracts as the seep evolves. The presence of life in such an environment opens the door to understanding the collaborative processes that underpin everything happening around these cold, steady flows rising from the seafloor. In the regions where seep fluids rise from the seafloor, everything that lives there must confront a chemical reality that would overwhelm most known forms of life. The water contains hydrogen sulfide, methane, and a mixture of reduced compounds that interfere with the fundamental processes animals rely on to generate energy. Oxygen, where present, disappears quickly as soon as these chemicals begin to react. The animals living in these zones cannot depend on the same biochemical pathways that support typical marine species. They must anchor their survival to reactions that, under ordinary circumstances, would shut down metabolism entirely. Understanding how they accomplish this begins with examining what happens when these chemicals enter a living body and why nearly all organisms avoid them. Hydrogen sulfide presents the clearest challenge. In animals like humans, hydrogen sulfide disrupts the ability of cells to use oxygen by binding to key enzymes in mitochondria. These enzymes direct the chain of reactions that convert oxygen and nutrients into usable energy. When hydrogen sulfide interferes, cells can no longer extract energy efficiently. They suffocate at the molecular level, even if oxygen is present in the surrounding environment. The compound works quickly and leaves little room for physiological compensation. That is why animals adapted to oxygen-rich conditions cannot tolerate even small concentrations. In seep environments, however, hydrogen sulfide exists in far greater quantities. The animals living there must handle concentrations that would cause lethal damage elsewhere. The remarkable part is that they do not simply tolerate hydrogen sulfide, they use it. Their ability to do this depends on biochemical pathways that redirect the compound from harmful targets and deliver it instead to bacteria capable of oxidizing it. These bacteria reside inside the tissues of the animals, forming tightly integrated partnerships. In many ways, the animals act as controlled conduits, channeling hydrogen sulfide to their symbiotic partners and receiving nutrients in exchange. This process requires adaptations at multiple levels. The cells must avoid binding the toxic molecules, the circulatory system must distribute them carefully, and the bacteria must convert them efficiently enough to sustain the entire organism. Some seep animals rely on specialized hemoglobin molecules designed to bind both oxygen and hydrogen sulfide simultaneously. At the surface, this combination would cause interference, but in seep organisms, the hemoglobin structure prevents hydrogen sulfide from reacting with vulnerable cellular machinery. Instead, it shuttles the compound safely to tissues where the bacteria reside. The hemoglobin acts like a selective carrier rather than a simple oxygen transport molecule. Its ability to prevent toxic reactions explains how tube worms, for example, can thrive even when surrounded by concentrations of hydrogen sulfide that would incapacitate normal marine invertebrates instantly. Inside the tube worms, a specialized organ called the trophosome houses dense populations of bacteria. These bacteria break down hydrogen sulfide, using it as a fuel source through oxidation. As they metabolize the compound, they release nutrients that diffuse into the tube worm's tissues. The entire process replaces the need for a digestive system. Tube worms have no mouth or stomach because their energy supply comes entirely from the bacteria. The evolutionary investment in this partnership is so complete that tube worm larvae must acquire the bacteria shortly after settlement, otherwise they cannot grow into functioning adults. Mussels and clams at seep sites also rely on symbiotic bacteria, but their structures differ. These animals retain digestive systems, yet their nutritional dependence shifts dramatically toward their internal microbial partners. Their gills or specialized organs host bacteria capable of oxidizing methane or hydrogen sulfide. The animals regulate the flow of water and seep chemicals through their bodies, maintaining conditions that favor bacterial metabolism. When the bacteria produce nutrients, the mussels or clams absorb them. Their tissues reflect this shift. Biochemical analysis reveals that much of the carbon in their bodies originates from the byproducts of bacterial metabolism rather than from any ingested food. They can still feed on particles if necessary, but their primary survival strategy depends on chemical processing. Methane provides another key energy source in seep ecosystems. Most animals cannot use methane directly, but bacteria can oxidize it through pathways that release energy and produce organic molecules. These methane oxidizing microbes live on surfaces exposed to seep fluids and inside the tissues of mussels and clams. Their presence adds a second major pathway for chemical energy to enter the ecosystem. The animals hosting methane oxidizing bacteria occupy portions of the seep where methane concentrations remain stable, but hydrogen sulfide levels do not become overwhelming. This spatial separation reflects distinct physiological requirements. Hydrogen sulfide specialists cluster around sulfide-rich zones, while methane specialists occupy areas dominated by methane seepage. The ability of microbes to oxidize methane and hydrogen sulfide depends on enzymes not found in typical animal metabolism. These enzymes use oxygen, nitrate, or other electron acceptors to convert reduced compounds into less toxic forms. During the process, energy becomes available for cellular growth. Microbes near seeps often form thick mats where they carry out these reactions collectively. These mats become large enough to support grazing animals, linking microbial activity to higher trophic levels. Even though most animals cannot use the chemicals directly, the microbes transform them into accessible forms that extend the reach of chemical energy through the ecosystem. The chemistry of survival does not stop with symbiosis. Many seep animals must regulate internal conditions carefully to prevent damage from fluctuating chemical concentrations. Even small shifts in seep flow can change hydrogen sulfide levels dramatically. Tube worms compensate through adjustable blood flow and selective transport of molecules. Mussels regulate the opening and closing of their shells, adjusting exposure to the water. Clams extend their siphons only into portions of sediment where concentrations remain stable. These behavioural and physiological adjustments ensure that chemical intake remains within tolerable limits, even when the seep pulses or shifts slightly over time. The microbial partners also possess mechanisms to handle chemical stress. Their enzymes are structured to function efficiently in environments low in oxygen or with complete absence of it. Some bacteria perform anaerobic methane oxidation, using sulfate rather than oxygen as the electron acceptor. This reaction couples methane consumption with sulfate reduction, producing hydrogen sulfide in the process. It may seem counterproductive to produce a toxic compound while consuming another, but in the layered structure of seep environments, one organism's waste becomes another organism's resource. Hydrogen sulfide produced by methane oxidizing bacteria can then fuel sulfide oxidizing bacteria. These interconnected processes demonstrate how chemistry shapes the entire structure of the ecosystem. The organisms living around cold seeps also show adaptations to resist oxidative stress. Although the deeper portions of the environment remain low in oxygen, the boundary where seep fluid meets seawater experiences rapid chemical reactions, producing reactive oxygen species. These molecules can damage DNA, proteins, and membranes. Seep organisms possess enhanced antioxidant systems that neutralize reactive molecules before they cause harm. Their cells contain higher concentrations of protective enzymes and molecules capable of stabilizing cellular structures. This biochemical shielding allows them to function in an environment full of reactions that would overwhelm unadapted tissues. While the animals depend heavily on their bacterial partners, the bacteria also rely on the animals for access to conditions that favour growth. Tube worms, mussels and clams position themselves in gradients where fluid flow remains stable. They regulate water movement around the bacterial tissues, ensuring fresh supplies of chemicals and removing waste products. This controlled environment allows the bacteria to perform chemical reactions efficiently, preventing local buildup of toxic intermediates. The animals in turn benefit from the nutrients produced by the microbes. The balance requires precise positioning, consistent flow, and a stable relationship between host and symbiont. The chemistry of survival extends into the physical environment surrounding the seep organisms. As hydrogen sulfide and methane enter the water, they undergo chemical reactions with minerals in the sediment. These reactions can produce carbonate rock, forming structures that reinforce the area around seeps. These carbonate formations create stable surfaces for organisms to anchor themselves. Tube worms often grow around the edges of these hard substrates because they need firm attachment points in regions where sediment might otherwise shift. Mussels cluster on carbonate surfaces as well, forming dense aggregations that remain stable even in areas with slow-moving currents. The chemical reactions that produce carbonate rock therefore contribute to the structural integrity of the ecosystem. Some seep organisms store sulfur compounds inside their tissues as a buffer against fluctuating environmental concentrations. This stored sulfur can be oxidized when external hydrogen sulfide levels drop temporarily, allowing continuous energy production by symbionts. When the seep strengthens again, the animals release stored sulfur or adjust their internal transport systems to prevent excess accumulation. This buffering ability demonstrates how organisms integrate chemical variability into their biological processes. The ability to survive in these chemically intense environments also depends on maintaining internal pH balance. The reactions involved in hydrogen sulfide oxidation and other metabolic pathways can produce acidic conditions. If not regulated, these conditions interfere with cellular processes. Seep organisms possess mechanisms to counteract pH shifts, including specialized ion exchange systems and metabolic adjustments. Their cells regulate ions such as bicarbonate and protons to stabilize internal conditions. These buffering systems work continuously to ensure that even during periods of rapid chemical reaction, the organism maintains a functional internal environment. Beyond the immediate energy pathways, seep organisms incorporate chemical signals into their development and behavior. Larvae searching for suitable settlement sites detect chemical gradients that indicate active seepage. These cues guide them toward regions where their future symbiotic partners can flourish. Once they settle, the larvae undergo metamorphosis that prepares them for life dependent on chemical intake. Tubeworm larvae, for instance, lose their digestive systems as they transition into adults because they will rely entirely on bacterial metabolism. This developmental transformation underscores how deeply chemical dependence is embedded in their biology. Over time, the chemistry of the seep environment shapes not only individual species, but the entire community. Species distributions reflect chemical concentrations. Areas with high hydrogen sulfide support sulfide oxidizing communities. Regions with stronger methane seepage support methane oxidizing communities. Transitional zones host mixed populations. The community structure merges geology with biology, drawing boundaries and arranging species according to the flow of energy through chemical reactions. This integration between chemical environment and biological adaptation highlights a broader principle. Survival depends on accessing energy, not necessarily on the form that energy takes. On the surface, sunlight drives nearly every ecosystem. In the deep ocean, chemical energy fills that role. The creatures at cold seeps show that life can build complexity around any consistent energy source, provided it can develop the biochemical tools to transform that energy into usable forms. The ability to breathe what would harm most organisms reflects a combination of microbial innovation, physiological specialization, and environmental consistency. It illustrates the extent to which life can adjust to unfamiliar conditions when the opportunity for energy exists. These adaptations set the stage for understanding how the organisms interact further, constructing communities rooted in chemical reactions rather than sunlight, and demonstrating how deeply the chemistry of the seep permeates every aspect of survival. In the deep regions where cold seep fluids rise steadily from the sediment, the first impression of the environment often centers on the chemistry, the darkness, and the slow steadiness of the surroundings. But once the basic nature of the seep becomes familiar, attention shifts to the communities built around it. These are not temporary gatherings or loosely arranged clusters. They are structured, layered, and shaped by the organisms that anchor themselves to the seafloor. The creatures living here do more than survive. They change the physical layout of the area. They create surfaces, shelter, and pathways that didn't exist before. Their presence turns a smooth plain of sediment into something that looks planned, even though the planning emerges from biological necessity rather than intention. The tubeworms and mussels act as builders, organising the space through growth and positioning in ways that define how the rest of the community develops. Before any structure appears, the seafloor exists as a flat or slightly undulating expanse of mud. The seep fluid rises through cracks and moves outward, forming the chemical gradients that attract microbial activity. The earliest arrivals in many seep areas are bacteria and archaea, spreading across the sediment in mats. These mats represent the first stage of construction, laying down the energy foundation that later organisms will depend on. But the larger architecture begins when tubeworm larvae or mussel larvae detect the chemical signature that signals an active seep. That signal tells them to settle. Once they attach, their presence changes everything around them. Tubeworms, which can grow from several centimetres to several metres tall depending on the species, become upright structures that dramatically alter the flow of water near the seafloor. Their tubes, made from secreted chitinous material, provide stability in sediment that might otherwise shift easily. When enough tubeworms gather in one place, they form dense clusters that resemble miniature forests. These clusters change how seep fluids emerge, how sediment settles, and how small animals navigate the area. The seep flow moves around the tubes, creating sheltered regions on the downstream side where other organisms can gather. Sediment begins to accumulate in patterns influenced by the tube's shape. What was once an open, unstructured surface transforms into a multi-layered habitat. The growth of tubeworms continues year after year, with individuals living decades or even centuries. Each new tubeworm adds another vertical column to the existing cluster. Over time, the base of the colony can become compacted with old tubes, dead tissue and mineral deposits resulting from the seep's chemical reactions. This creates a permanent substrate in a region where hard surfaces would otherwise be rare. Once this foundation develops, a wide range of organisms can attach to it, increasing the diversity of the community. Small crustaceans take shelter between the tubes. Fish hover near the edges of the clusters. Polychaete worms weave through the narrow spaces. The tube worms, without moving or behaving actively, become architects simply by existing. Their architecture extends below the surface as well. Tubeworms anchor themselves with root-like structures that penetrate the sediment. These structures position the worms in the exact chemical zone, where their symbiotic bacteria can access hydrogen sulfide efficiently. As the tubeworms extract sulfide from the sediment, the chemistry changes slightly, creating zones where different microbial communities flourish. The biological and chemical shaping occur simultaneously, each reinforcing the other. The growing tubeworm community therefore creates a vertically extended habitat, from the deeper sediment layers through the tubes rising above the seafloor. While tubeworms build upward, mussels build outward. Mussels at seep sites do not distribute themselves evenly. They form dense beds that can extend across dozens of square meters. Each mussel attaches to the substrate or to neighboring shells using byssal threads. These threads help stabilize the entire group, preventing individuals from being pushed out of position by slow but persistent deep-sea currents. As more mussels join the cluster, the bed becomes a cohesive structure. Spaces between shells form channels that allow water and seep fluid to move through in ways that expose the mussel gills to the chemicals their symbiotic bacteria require. In this sense, the mussel bed operates like a porous living filter system arranged to maximize chemical processing. The mussel beds also alter the physical environment around them. The accumulation of shells elevates portions of the seafloor, creating topography in a landscape that otherwise lacks variation. These elevated sections provide surfaces for microbial mats to grow, and they create pockets where small animals find shelter or search for food. Some seep fish patrol around mussel beds regularly, attracted by the abundance of smaller invertebrates that live among the shells. The mussels, through continuous growth and shell deposition, extend the boundaries of the usable habitat, drawing in organisms that would not have settled in the area otherwise. The mussel shells themselves influence the seep environment chemically. As they grow, the mussels incorporate minerals into their shells, including carbonates precipitated from the reactions between seep chemicals and seawater. The build-up of carbonate material around mussel beds reinforces the substrate further. Hard carbonate structures provide additional anchoring points for other organisms and help stabilize the seep area against shifting sediment. These processes demonstrate how biological activity becomes inseparable from geological change. The mussels reinforce the area where the seep flows rise, making the habitat more suitable for long-term community development. Meanwhile, clams contribute their own architectural impact. Although they bury themselves rather than forming visible structures above the sediment, their presence changes the seafloor texture. The constant movement of water through their siphons, combined with the chemical reaction surrounding their bodies, affects sediment chemistry and stability. In large numbers, clams can modify the upper layers of sediment, creating a mixed zone where different chemical gradients overlap. This mixed zone becomes suitable for specific microbial groups, which in turn attract animals that feed on them. Although less obvious than tubeworm clusters or mussel beds, the clam communities contribute to the layered design of seep habitats by reshaping subsurface structure. The architectural roles of seep organisms emerge more clearly when considering how long these communities persist. A seep may remain active for centuries, allowing structures to accumulate and evolve. Tubeworm clusters may reach heights that drastically alter local currents. Mussel beds may become so dense they form continuous expanses that redefine large areas of seafloor. The stabilizing carbonate deposits may create rigid foundations, where previously only soft sediment existed. All of these features accumulate slowly, reflecting the pace of life in the deep sea. They grow in small increments year after year, producing long-lasting results that define the entire ecosystem. Small organisms also contribute to the architectural landscape. Crustaceans burrow into sediment or move through mussel beds, creating small tunnels or chambers that enhance water flow around the community. Polychaete worms build tubes that provide microhabitats for other small creatures. Grazers leave trails across bacterial mats, altering the distribution of microbial hotspots. Each action adds subtle structural changes. Although these changes may appear minor individually, in aggregate they influence how water moves, how sediment settles, and how chemicals diffuse. The cumulative effect contributes to the complexity of the entire seep community. The animals do not construct these environments intentionally, but the outcome resembles intentional design because every adaptation aligns with the chemical requirements of survival. Tubeworms build vertically to reach the precise zones where sulfide meets oxygen. Mussels cluster tightly because the proximity ensures access to seep chemicals while maintaining structural stability. Clams bury themselves at specific depths to balance chemical intake and protection from predators. Together, these strategies produce communities that look engineered, even though they emerge from natural selection and environmental constraints rather than planning. The structures created by these organisms also influence how future generations settle. Larvae moving through the deep ocean detect chemical cues that guide them toward active seeps. But once near a seep, the presence of tubeworm colonies or mussel beds provides additional signals. Dense structures indicate that the seep has been stable for a long period, suggesting that it may continue to provide the chemical flux needed for survival. These signals encourage larvae to attach and begin their development. In this way, the architecture of the community reinforces its own persistence by guiding new organisms towards suitable sites. In some regions, seep communities grow so extensively that they merge with others, forming complex mosaics of mussels, tubeworms, clams, and microbial mats. The boundaries between these groups shift slowly as seep flow patterns change. When a seep weakens, tubeworms may experience reduced growth, mussels may relocate if possible, and microbial mats may thin. In areas where flow increases, new organisms may settle and expand the community. The architecture adjusts to these changes, but the underlying structural influence remains strong as long as some seep activity persists. These communities underscore the idea that life in the deep ocean functions not only through survival, but through modification of the environment. The organisms living at cold seeps do not merely occupy space, they shape it. They change the flow of chemicals, alter sediment stability, and create three-dimensional structures in a region otherwise defined by flatness. Their collective activity builds a landscape that supports a broader range of life than the initially barren seafloor could provide. Understanding the architectural roles of tube worms and mussels reveals how deeply the ecosystem depends on structural complexity. The physical design of the community influences how energy moves, how species interact, and how long the system remains stable. Each structure represents a response to the chemical conditions, and together they transform those conditions into a habitat rich enough to support diverse organisms. This built environment continues to evolve as the seep changes, linking biological growth to geological processes in a slow but continuous cycle that defines life in these deep, steady pockets of the ocean. In every corner of a cold seep community, no matter how large the animals appear or how intricate the structures they form, the real foundation lies hidden inside tissues, beneath shells, and across the sediment surface in layers too thin to notice at first glance. The flow of energy in these environments begins not with the animals themselves, but with the microbes that convert seep chemicals into usable forms. These microorganisms handle reactions that would overwhelm normal physiology, transforming hydrogen sulfide, methane, and other reduced compounds into nutrients that support the entire community. Their presence explains how large tubeworm forests, dense mussel beds, and thriving clam fields can exist without sunlight or conventional food sources. The microbes act as engines, unseen but indispensable, guiding every breath, every pulse, and every growth event in the seep ecosystem. These microbial engines form multiple groups, each specializing in a particular chemical pathway. Some focus on oxidizing hydrogen sulfide, others process methane. Some carry out both reactions under different conditions, shifting strategies based on which chemicals are available. The animals hosting these microbes depend on this flexibility. A small change in seep flow, slight increases in sulfide or methane, subtle shifts in oxygen availability, can alter the microbial balance, which in turn affects how well the animals can maintain their energy supply. Understanding the symbiosis means understanding not only which microbes are present, but how they adjust to these ongoing changes. The hydrogen sulfide oxidizers typically operate in zones where seep fluid meets seawater, because the reaction requires both sulfide and an electron acceptor such as oxygen or nitrate. These microbes live inside tubeworm trophosomes, on the gills of clams, and in layers coating the sediment. When hydrogen sulfide contacts their metabolic machinery, they oxidize it step by step, releasing energy during the process. This energy becomes the fuel that powers cellular activity, allowing the microbes to build biomass and produce nutrients. The animals benefit because they absorb the nutrients directly or receive them through specialized internal systems that transfer microbial byproducts into their own tissues. Inside tube worms, the relationship with these microbes is so complete that the worms no longer maintain a digestive system. Their internal biology revolves around housing and supporting their microbial symbionts. The trophosome where these microbes live is loaded with blood vessels carrying both oxygen and hydrogen sulfide. The tubeworm circulatory system delivers the chemicals at controlled rates, allowing the bacteria to work steadily without overwhelming the tissues. The worms themselves perform no digestion. Their survival depends entirely on microbial metabolism. Even their growth rates, which stretch over decades or centuries, reflect how efficiently the microbes process the seep chemicals. In mussels and clams, the microbes occupy different tissues but play similar roles. Mussels house methane oxidizing or sulfide oxidizing bacteria in their gill tissues. These bacteria form compact communities within specialized cells that regulate their chemical environment. As methane or hydrogen sulfide passes over the gills, the microbes absorb these molecules and begin metabolic processing. The energy produced sustains both the microbes and the host. The mussels also retain their ability to filter feed when necessary, but in stable seep environments, the majority of their nutrition comes from microbial partners. The shift from external feeding to internal chemical energy shows how strongly the symbiosis influences their biology. Clams adopt an approach similar to mussels, but maintain more separation between microbial and animal tissues. Their gills contain symbionts able to oxidize sulfide or methane. Their bodies regulate the flow of water and sediment, directing chemical-laden fluids toward the gills at rates that sustain microbial activity. The microbes then produce nutrients absorbed by the clam's tissues. This process can dominate the clam's metabolism to the point where traditional feeding becomes secondary. Some clam species appear nearly fully reliant on their microbial partners, blurring the boundary between animal and microbial functions. Beyond the large, obvious animals, microbial communities cover the sediment surface in mats that often appear as pale patches, dark stains, or thin films. These mats form where seep fluids consistently reach the seafloor. The microbes growing there carry out the same oxidation reactions as those inside animals, but the mats operate independently. Their growth rate depends directly on the supply of seep chemicals. Where seep flow strengthens, the mats thicken. Where it weakens, the mats shrink. These mats represent the first stage in the nutrient chain that supports small grazers, which then support larger predators. Even without hosting microbes internally, many seep animals rely on microbial mats as their primary food source. Some microbial groups operate with little or no oxygen. These anaerobic methane oxidizers perform one of the most significant chemical processes in seep ecosystems. They use sulfate instead of oxygen to oxidize methane, producing hydrogen sulfide in the process. This reaction not only consumes methane before it enters the water column, helping regulate methane flow into the ocean, but also supplies sulfide that other microbes can use. The result is a looping chemical cycle in which one microbial group's waste becomes another group's energy source. This cycle keeps the seep environment chemically active even in regions where oxygen is scarce. The anaerobic microbes commonly form partnerships with sulfate-reducing bacteria. Together, they create consortia, tightly linked groups that exchange molecules directly. Their interactions occur on extremely small scales, but influence community-wide chemical dynamics. When methane concentrations rise, these consortia expand, slowing the methane spread through the sediment. Their activity helps stabilize the chemical boundary where seep fluid meets seawater, forming predictable zones where larger organisms settle. These microbes therefore participate indirectly in shaping the architecture of the community by controlling chemical gradients that dictate organism distribution. Symbiotic microbes also respond to shifting seep activity in ways that allow the animals to function in fluctuating environments. If hydrogen sulfide levels drop temporarily, some microbes switch to alternative pathways using stored sulfur compounds inside the host. If oxygen levels decline, microbes adjust metabolic rates or shift to reactions requiring nitrate instead. These responses allow the symbiosis to remain stable despite environmental variability. The animals depend on this flexibility because their survival hinges on continuous energy flow. Any prolonged interruption would challenge their ability to grow, reproduce, or even maintain basic physiological functions. The stability of these microbial communities underscores how tightly evolution has shaped their interactions with host animals. The microbes do not simply live alongside the animals, they occupy specific tissues, receive carefully regulated supplies of chemicals, and provide nutrients in return. This exchange defines the biology of the animals. Without the microbes, the animals could not survive. Without the animals, the microbes would not gain access to the precise chemical conditions they require. The two partners form integrated metabolic systems, working together to harness chemical energy in an environment devoid of external food sources. These microbial partnerships also influence the long-term evolution of the seep animals. Tube worms, mussels, and clams all display traits reflecting their reliance on symbionts. Their gill structures, circulatory systems, developmental pathways, and metabolic controls have shifted to accommodate the presence of microbes. Even their reproductive strategies adapt to maintain the symbiosis. Tube worm larvae acquire symbionts shortly after settlement, initiating the metabolic system they will depend on for life. Mussels pass symbionts to new generations through tissues capable of hosting early microbial colonization. These processes demonstrate that the symbiosis not only supports adult life, but also directs how new individuals develop. The microbial engines power the seep communities beyond direct energy pathways. They also contribute to the chemical and geological shaping of the environment. As they oxidize sulfide and methane, they produce byproducts such as sulfate, carbonate, and elemental sulfur. These compounds accumulate in the sediment and contribute to mineral formation. Carbonate precipitates create hard substrates that provide attachment points for mussels and tube worms. Elemental sulfur deposits may form patches of bright yellow sediment in certain areas. The microbes indirectly reinforce the physical structures that define the seep habitat. The influence of symbiotic microbes extends further when considering nutrient recycling. Many seep organisms produce waste that microbes can process. These microbial reactions release nutrients back into the environment, creating localized cycles that support additional growth. Small organisms feed on the microbial mats generated in these recycling zones. Larger organisms feed on those small creatures. The microbial transformations thus provide the foundation for multiple food chains, operating simultaneously within the seep. Their presence also affects how the seep ecosystems respond to long-term environmental change. As seep flow strengthens, microbial communities expand, creating larger zones where animals can settle. When seep flow weakens, the microbial populations contract, reducing the areas suitable for animals. Because the microbial communities form the base of the entire ecosystem, they control the rate at which seep habitats grow or decline. Their responses to changing chemical conditions determine how quickly the rest of the community adjusts. Although these microbes are microscopic, their influence is widespread and persistent. They govern energy flow, shape habitat structure, regulate chemical gradients, and support the life cycles of animals many times their size. Every tubeworm's growth, every mussel's respiration, and every clam's metabolic process depends on the microbes performing chemical reactions on their behalf. Even the animals that do not host microbes internally still rely on microbial mats and chemical transformations for food. Understanding the seep communities requires recognizing that the visible organisms represent only part of the ecosystem. The microbes form the hidden half. Their chemical reactions create the conditions necessary for the animals to function. Their partnerships with hosts define how those animals live. Their influence shapes not only biological interactions but geological ones. They operate continuously, converting the chemical flows rising from the Earth's crust into energy that supports life in a world without sunlight. Their activity sets the pace and structure of the community, ensuring that even in the deep, cold waters of the ocean, complex ecosystems can emerge and persist through time. In areas where cold seeps release steady streams of methane into the surrounding sediment and water, the chemical landscape begins to accumulate traces of reactions that mark the history of the seep. These traces often remain invisible during a first pass across the seafloor. Only with closer examination does the full picture become clear, revealing deposits, particles, and layered structures that form slowly over years. Some of these deposits resemble drifting flakes, subtle and pale. Others take shape as sturdier mineral patches forming under the sediment surface. These features do not float through the water like the snowfall familiar from surface environments, yet the comparison fits because they settle gently, accumulate gradually, and create marks of chemical activity that remain long after the seep flow weakens. This persistent accumulation of methane-derived material helps define the system's long-term structure and signals where life has taken root. The idea of methane snowfall begins with methane itself. When methane escapes from the sediment into the water column, it enters a zone where temperature and pressure conditions allow it to combine with water molecules. Under the right circumstances, methane forms solid hydrates, crystalline structures that resemble ice but contain methane trapped within. On the seafloor near active seeps, these hydrates may form beneath the sediment or within pores where the seep flow is strongest. In some cases, methane bubbling upward destabilizes hydrate layers, causing small fragments to break apart and drift through the water or collapse into the surrounding sediment. When scientists refer to methane snowfall, they describe these tiny particles of hydrate that detach and settle like slow-moving flakes. The term emphasizes the gentle, persistent way these particles accumulate over time, adding to the layered record of seep chemistry. These hydrate fragments do not create dramatic changes in the environment by themselves, but their presence signals specific conditions: high methane concentrations, stable temperature gradients, and pressure levels that support crystallization. The organisms living nearby may not interact directly with the hydrate particles, yet the hydrates reveal the extent and strength of seep activity. Over time, these particles break down, releasing methane back into the chemical mix and continuing the cycle of microbial metabolism. They represent a form of temporary storage, capturing methane in solid form and then releasing it gradually as conditions shift. Beneath the surface, methane interacts with sulfate present in seawater, producing bicarbonate and hydrogen sulfide through the activity of anaerobic methane oxidizing microbes. This reaction increases carbonate concentration in the sediment, leading to the formation of minerals that solidify into carbonate rock. These carbonate structures can remain hidden beneath layers of mud, or they can form visible crusts that rise slightly above the seafloor. Over time, the repeated accumulation of carbonate creates an archive of chemical activity. This archive preserves the record of seep metabolism, marking where methane once flowed strongly and where microbial communities thrived. These accumulations are sometimes referred to as carbon ghosts, silent remnants of chemical processes that continue even after the seep itself shifts or weakens. The carbon ghosts take various forms depending on the mineral composition and the duration of seep activity. In some sites, the carbonate forms thin, fragile crusts that break easily under pressure. In others, it forms solid blocks capable of supporting mussel beds and tubeworm clusters for decades. The distribution of these carbonates reveals how the seep has evolved over time. Areas with thick, sturdy carbonate indicate long-term, stable chemical flow. Thin, fragile deposits suggest more variable activity. By studying these patterns, scientists reconstruct the history of seep usage, tracing the stages of microbial and animal colonization. These carbonate deposits also influence the biological community directly. Mussels need firm surfaces for attachment. Tubeworms require stable anchoring points in regions where sediment might otherwise shift. Carbonate rock created through methane oxidation provides the necessary substrate. Over time, these carbonate deposits become the foundation for entire communities, turning ephemeral chemical signals into durable habitats. Without carbonate formation, many seep communities would lack the physical stability required for long-term development. As the layers of carbonate accumulate, they sometimes trap traces of older microbial mats, preserving them in thin bands. These bands form chemical fingerprints that reflect the conditions under which the microbes lived. By analysing them, researchers can determine which microbial reactions dominated the environment at different times. The chemical signatures act like a timeline etched into the rock, documenting the rise, peak, and decline of the seep. The presence of these preserved layers shows how deeply the microbes shape not only the living community, but the geological record. Methane snowfall and carbon ghost formations therefore serve as ongoing indicators of seep processes. They mark regions where methane concentration remains high, where microbial activity operates intensively, and where animals gather in large numbers. Even when the animals themselves die, leaving behind shells or empty tubes, the carbonate deposits remain. These structures help future generations of organisms find places to settle. They also guide researchers studying how seep ecosystems expand, contract, and transform in response to shifting geological conditions. Another feature associated with methane snowfall is the presence of methane bubbles rising slowly through sediment columns. These bubbles may escape into the surrounding water or become trapped beneath carbonate layers. When trapped, they create pockets that eventually collapse or release their contents, adding another pulse of methane to the water. Each release fuels microbial reactions that generate more carbonate. This cyclical pattern, methane escape, microbial consumption, carbonate formation, creates a feedback loop that strengthens the physical structure of the seep habitat. The stability of this process depends on temperature, pressure, and sediment characteristics. Hydrate formation, for instance, requires conditions that remain consistent over time. If the temperature rises slightly, or if pressure decreases unexpectedly, hydrates can destabilize. When hydrates dissolve rapidly, they release methane in larger quantities, shifting the balance of the seep. These sudden pulses influence microbial activity and may alter the distribution of seep organisms temporarily. Over longer periods, such changes contribute to the shaping of carbon ghost structures in new layers. Chemical gradients in seep areas also interact with carbonate formation. In zones where sulfate concentration remains high, methane oxidation proceeds rapidly, producing more carbonate. In regions where sulfate becomes depleted, the carbonate formation slows, leading to gaps in the record. These gaps reflect periods of reduced seep activity or shifts in fluid pathways. The carbon ghosts left behind become markers of these fluctuations. The organisms living around cold seeps occasionally interact indirectly with methane snowfall and carbonate deposition. For instance, the presence of carbonate increases habitat complexity, giving animals more surfaces to occupy. Clams burrow around carbonate blocks, creating new sediment pathways. Small crustaceans use cracks in the carbonate for shelter. Microbial mats colonize the surfaces of carbonate formations, creating new feeding opportunities. These interactions transform the carbonate deposits into functional elements of the seep ecosystem rather than static geological features. The enduring presence of carbon ghosts reveals a striking aspect of cold seep biology. The environment records its own history. The chemical processes driving the ecosystem do not disappear without a trace. Instead, they leave behind structures that preserve the details of microbial metabolism and animal occupation. These preserved features allow scientists to understand how long a seep has been active, how strong the fluid flow was at different times, and how the community shifted in response. The geological record becomes a companion to the biological one, giving a full picture of how life and chemistry interplay over long timescales. Because the deep ocean changes slowly, these methane-derived deposits remain stable for centuries. Even after seep flow decreases, the carbonate structures remain intact. Animals may leave the area, but the carbon ghosts mark where they once lived. Eventually, new seeps may open nearby, attracting new organisms, and the carbonate structures may become part of a larger patchwork landscape shaped by successive generations of seep activity. The old deposits remind researchers that the seep environment has always been dynamic, even if the changes unfold over decades or centuries rather than years. This long-term perspective reveals a deeper insight into how seep ecosystems operate. They are not temporary gatherings built solely around current chemical conditions. They are part of an evolving geological system shaped by energy emerging from deep beneath the seafloor. The methane snowfall illustrates how chemical reactions create physical deposits. The carbon ghosts demonstrate how these deposits accumulate and persist. Together, they show how chemical forces shape both the biological community and the long-term geological foundation supporting it. Understanding methane snowfall and carbon ghost formation becomes important for interpreting the full picture of seep ecosystems. These features tell more than the story of current conditions. They highlight the cycles of activity and dormancy that govern the habitat. They reveal how layers of chemical history build upon each other. They show how the unseen processes of microbial metabolism shape the landscape, and they demonstrate how life at cold seeps depends not just on immediate chemical availability, but also on deeper geological rhythms that leave their marks through these persistent, silent accumulations. In the deep regions where cold seep communities gather around flows of methane and hydrogen sulfide, most of the attention gravitates toward the tubeworm clusters, mussel beds, microbial mats, and clams that build the core of the ecosystem. These organisms define the architecture, shape the chemistry, and anchor the energy supply that sustains the entire environment. Yet the story of the seep community becomes more complete only when considering the animals that do not stay permanently, the ones that drift through, linger briefly, or integrate into the margins without depending fully on the chemical engines below. These predators, wanderers, and occasional visitors add movement, risk, and unpredictability to a system otherwise defined by slow steadiness. Their presence demonstrates that even in a world built on chemical stability, interactions among species carry layers of complexity that unfold in subtle but meaningful ways. The first group to consider includes predators that make their living in the seep environment but do not rely on microbial symbionts or chemical processing. These animals feed on the organisms that do depend on the seep. They patrol mussel beds, slip through tubeworm clusters, or sift through sediment in search of prey. Some of them visit frequently, while others move between seeps as part of a broader hunting range. Unlike the symbiotic species anchored to specific chemical gradients, these predators remain more flexible. They respond to the presence of abundant prey rather than to the chemical cues rising from the seafloor. One example comes from fish species that hover around seep communities. These fish are not unique to seeps, and many of them live successfully in deep-sea environments far from chemical flows, but they are attracted to the high density of organisms at active seeps. The mussel beds provide hiding places for small crustaceans and worms. The bacterial mats attract grazers, which in turn attract larger animals. The fish take advantage of this concentration, moving slowly through the area and snapping at anything small enough to swallow. Their constant motion contrasts with the stillness of the seep animals, giving the community an additional layer of activity. Some seep-associated fish remain local once they discover a productive site. Others appear only occasionally, suggesting broad foraging routes. Their visits often follow patterns of deep-sea currents or seasonal movements, although they remain unaffected by light or temperature changes that govern surface ecosystems. Instead, they rely on chemical traces, prey availability, and perhaps subtle vibrations caused by the larger animals moving within the seep structures. The fish become part of the ecosystem's dynamic, without anchoring themselves to the chemical foundations that underpin it. In addition to fish, larger crustaceans play a significant role as predators and scavengers. Some species of decapods move through seep environments regularly, using their claws to pick apart mussel shells, pry open clams, or capture smaller invertebrates. Their presence can leave identifiable marks. A partially broken shell or scattered remains of a clam bed may indicate predation rather than environmental stress. These crustaceans do not stay permanently, they drift in, feed, and continue elsewhere. Their impact becomes clear when observing how mussel beds respond. Densely packed mussels create a barrier to entry, making it harder for predators to reach the individuals in the middle of the cluster. The outer edges, however, remain vulnerable. As predators attempt to feed on these edges, the mussel beds develop shifting boundaries influenced not just by chemical availability, but also by biological interactions. Wanderers represent a different category. These animals do not prey heavily on seep residents, but pass through the environment as part of larger journeys. Some deep-sea species follow currents or broad migration routes shaped by factors unrelated to the seep. They encounter the seep environment incidentally, perhaps remaining for a short time before continuing. Their presence is difficult to predict, often appearing sporadically in the recordings from remotely operated vehicles and submersibles. They include certain species of fish, gelatinous animals drifting in mid-water, and even deep-sea sharks in rare cases. These animals interact minimally with seep organisms but contribute to the sense that the deep ocean remains connected even across vast distances. Occasionally, octopuses appear around cold seeps. They do not depend on the chemical foundation of the ecosystem, but some species find the physical structures suitable for shelter. Mussel beds provide small crevices. Tubeworm clusters offer places to hide from larger predators. The presence of octopuses adds another layer of interaction. They may feed on small crustaceans or clams. They may simply rest before moving onward. Their behaviour introduces moments of motion more rapid than the usual slow sweeping of fish fins or the drifting current. While they rarely stay for long periods, their visits underscore the point that seep communities do not exist in isolation. They are connected to a broader ecological network that extends far beyond the chemical boundaries of the seep. Sea stars, too, find opportunities in seep environments. Some species adapted to deep waters slowly move across mussel beds, feeding on bivalves or scavenging remains left by other predators. Their slow movements align with the pace of the seep itself, making them consistent but not overwhelming parts of the ecosystem. Their presence shapes mussel bed distribution by influencing survival on outer edges. In areas where sea star density increases, mussels may cluster more tightly or shift toward more chemically favourable zones where predators move less frequently. Another group of visitors includes animals that feed specifically on bacterial mats. These grazers may not contribute directly to symbiotic pathways, but they rely on microbial production for nourishment. Snails, small worms, and amphipods often populate the edges of microbial mats, scraping away surface layers as they move. Their grazing influences the distribution and thickness of microbial communities. By removing older or denser patches, they create uneven surfaces where new microbial growth can flourish. In this way, the grazers act as regulators, preventing microbial mats from reaching levels that would reduce oxygen penetration or disrupt the chemical exchange essential to deeper layers of microbes. The grazers themselves attract predators, creating localized food chains within the seep system. Even though these chains do not reach the complexity of surface ecosystems, they show that the flow of energy extends beyond primary chemical reactions and creates opportunities for multiple levels of biological interaction. Some grazers drift widely across the seafloor, encountering multiple seeps in their lifetimes. Others remain near stable seeps, where microbial mats persist for long periods. Their patterns influence how microbial layers grow and how the larger community maintains balance between chemical and biological processes. In addition to predators and grazers, scavengers contribute to the movement of nutrients and the redistribution of organic material. When animals die within the seep, their bodies become immediate targets for scavengers. Crabs, amphipods, and certain fish species gather quickly to consume soft tissues. This rapid consumption prevents large amounts of organic material from accumulating and altering the chemical balance of the area. The presence of scavengers ensures that the seep environment remains relatively stable, with nutrient recycling occurring consistently. Their activity helps prevent sudden chemical shifts that could disrupt microbial communities or harm symbiotic organisms. Some visitors remain difficult to categorize because their connections to seep environments appear incidental rather than essential. These include jelly-like organisms drifting through the water column. They interact minimally with the seep, but occasionally become part of the system when they drift too close, providing food for opportunistic predators. Their presence shows how vertical and horizontal movement throughout the deep ocean can bring a wide range of species into temporary contact with seep communities. These encounters rarely last long, but they reveal that seep ecosystems remain open to outside influence even when their core components remain highly specialized. Crabs provide an especially interesting example of flexible ecological roles in seep environments. Some species act as predators, others as scavengers, and still others as opportunists feeding on microbial mats or detritus. Their versatility allows them to exploit multiple resources within the seep. They move between tubeworm clusters, climb across carbonate structures, and position themselves on the edges of mussel beds. Their behaviour influences where smaller animals gather and how microbial mats develop. Crabs often appear in video footage as active movers, adding visible dynamism to an otherwise calm setting. Their presence reinforces the idea that seep ecosystems, while slow in many respects, contain areas of rapid activity brought on by animals that do not depend directly on chemical symbiosis. While predators and wanderers add motion and unpredictability, they also create pressure on the seep community. Predation influences which animals flourish and how densely they gather. In areas with high predator activity, mussel beds may shrink or become more tightly clustered. Tube worms, protected by hard tubes, endure predation better, but their larvae and juveniles remain vulnerable. These interactions create shifting patterns over decades, gradually reshaping the balance of species. The seep does not undergo sudden changes based on predation alone, but the cumulative effect contributes to the long-term evolution of the community. Migratory animals occasionally appear near seep environments. Some deep-sea fish species undergo vertical migrations linked to feeding or reproductive cycles. When these animals descend into the depths, they sometimes pass over seep sites. The chemical signatures of the seep do not draw them directly, but the abundance of prey may hold them briefly before they continue. Their visits may occur at intervals too long for researchers to observe frequently, but each appearance adds another layer to the image of the seep as a place intersected by many different life paths. Another type of visitor consists of larval stages of animals that do not remain in seep habitats as adults. Deep-sea currents carry larvae through these zones, exposing them to chemical cues, physical structures, and microbial mats. Most larvae drift onward without settling, but their temporary presence demonstrates that seep environments participate in the broader circulation of oceanic life, influencing species even when those species do not integrate fully into the seep system. Even some animals typically associated with hydrothermal vents may appear at cold seeps under certain conditions. While vents and seeps differ fundamentally in temperature and flow characteristics, the animals navigating between them sometimes encounter both. If a vent-associated species wanders into a seep, it may explore briefly before leaving due to mismatched environmental requirements. Such occurrences emphasize that the boundaries between deep-sea habitats are not absolute. Species explore, migrate, and shift ranges based on food availability, currents, and unique circumstances. Taken together, the predators, wanderers, and odd guests moving through cold seep environments reveal that these ecosystems, though anchored in chemical energy, remain part of a broader deep ocean network. They do not function as isolated chemical islands. The core community depends on symbiosis and precise chemical gradients, but the surrounding ecosystem involves interactions with species that follow entirely different survival strategies. These interactions create subtle pressures, new opportunities, and varying levels of influence across the community. Over decades and centuries, these visitors shape the pattern of the seep environment. Predators influence population density. Wanderers introduce occasional disturbances. Scavengers maintain chemical stability by processing organic material rapidly. Grazers control microbial mats. Each group interacts with the seep community differently, but all contribute to its long-term structure. Understanding these interactions highlights a broader truth about deep-sea ecosystems. Even in places defined by slow processes and chemical steadiness, the biological community remains dynamic. Movement, predation, exploration, and brief encounters all play roles in shaping the life that gathers around the seep. These subtle interactions ensure that the ecosystem functions not only as a chemical engine, but also as a biological network where species intersect, influence one another, and contribute to patterns that continue long after individual organisms move on. When a cold seep first becomes active, it transforms a quiet stretch of seafloor into a slow but steady centre of biological activity. Microbes gather, tube worms settle, Mussels expand, clams burrow, predators explore, and carbonate structures begin forming beneath the sediment. For decades or centuries, the seep maintains this rhythm, supplying methane and hydrogen sulfide at rates that sustain entire communities. But every seep has a lifespan shaped by the geological forces beneath it. Eventually the chemical flow weakens, shifts, or stops entirely. When that happens, the community above must adjust to diminishing resources in a way that mirrors the long, quiet pacing of life in the deep sea. The decline does not begin with rapid collapse. It unfolds slowly, reflecting the steady processes that built the ecosystem in the first place. The earliest signs of a weakening seep often appear not in the behaviour of the animals, but in the chemistry of the sediment. Slight drops in hydrogen sulfide concentration occur near tubeworm roots. Methane levels fall in regions where mussels feed their symbionts. Microbial mats begin thinning at the edges, responding immediately to reduced chemical availability. These changes are subtle enough that only detailed measurements reveal them, but they alter the internal environment of the animals in ways that grow increasingly significant over time. The core organisms depend directly on the seep's chemical supply. When the supply falters, they must compensate, slow their metabolic rates, or adjust their positions along the gradient. Tubeworms, for example, rely entirely on their internal symbiotic bacteria to convert hydrogen sulfide into nutrients. If the sulfide concentration drops too far, the bacteria cannot maintain the same output. The tubeworm's growth slows. Some individuals may stop expanding entirely, maintaining only basic survival functions. Tubeworm colonies that once stood tall and dense may begin showing uneven spacing as younger or weaker individuals fail to keep up. This thinning mirrors the gradual decline of the seep. The worms cannot relocate, so their fate ties directly to the chemical conditions beneath them. Over years, their once thriving forests become sparser, leaving gaps where the chemical flow no longer supports growth. Mussels respond differently because they retain some capacity for mobility. Although they cannot travel great distances, they can detach from their positions and re-anchor themselves in regions where seep flow remains stronger. In declining seeps, mussels sometimes shift to the edges of the community, clustering in areas where residual seepage still reaches the seafloor. These small shifts do not save the entire colony, but they prolong survival for the individuals capable of relocating. Mussel beds gradually thin from the centre outward, leaving behind shells that once formed dense structures. Over time, these abandoned shells accumulate as evidence of the bed's former size, forming layers that later help researchers determine how long the seep was active. Clams, buried beneath the sediment, face a different challenge. They must balance depth with chemical intake. As seep flow drops, the zone containing sufficient chemical concentration retreats deeper into the sediment or disappears entirely. Clams cannot burrow indefinitely, and even if they could, the diminishing sulfide or methane would eventually fall below the threshold needed to sustain their symbionts. As a result, clam populations decline gradually. Shells begin to appear on the seafloor surface as the animals die, are consumed by scavengers, or leave behind empty remains that become incorporated into the sediment structure. Their disappearance further reflects the seep's weakening state. Microbial mats undergo more rapid changes than animals. Since microbes react immediately to chemical availability, their thinning or disappearance can occur within weeks or months. The colourful patches of bacterial growth fade into paler films, then into scattered spots, and eventually vanish from large sections of the seep. Without the bacteria that form the first layer of energy processing, small grazers lose their primary food source. Amphipods, snails, and worms leave the area, shifting toward the periphery or moving into unrelated habitats. Their departure removes an entire section of the food chain, influencing the behaviour of predators that once relied on them. Predators, which do not rely directly on the seep chemistry, respond primarily to the decline in available prey. Fish that once hovered around mussel beds drift away to search for other productive areas. Crabs that used to scavenge among the shells appear less frequently. Sea stars reduce their visits as mussel and clam populations shrink. The decline in predators occurs gradually, mirroring the slow fading of the seep's energy supply. They leave no dramatic signal, but their absence becomes clear when researchers compare video footage taken across decades. Even the carbonate structures beneath the sediment reveal changes as the seep weakens. Carbonate forms when microbial reactions convert methane into bicarbonate, which then precipitates into solid minerals. When methane flow declines, carbonate formation slows and eventually stops. The existing carbonate deposits remain, but they no longer grow. In some areas, they begin to erode as sediment shifts or currents reshape the seafloor. These carbonate remnants serve as geological signatures of past seep activity, long after the biological community has disappeared. Their presence helps identify former seep sites, even when no living organisms remain to mark the area. As seep activity declines further, the entire ecosystem transitions into a dormant state. Tube worms that cannot sustain themselves gradually die, leaving behind their tubes as hollow structures. Mussel shells accumulate on the seafloor, forming deposits shaped by currents and scavengers. Clam shells mix with sediment layers. Microbial mats leave faint chemical imprints or thin mineral coatings that signal where they once grew. The overall community loses density and structure, returning slowly toward the more uniform landscape that existed before the seep became active. Yet even in this decline, life persists in pockets. Some microbes survive in low-energy environments by slowing their metabolism dramatically. They remain in the sediment, capable of responding quickly if seep flow resumes or a nearby crack opens. Scavengers continue processing the organic remains left behind, ensuring that the area's chemistry does not shift abruptly due to decomposing material. The decline phase becomes a gradual transition rather than an abrupt end. Eventually, the seep may stop emitting detectable amounts of methane or hydrogen sulfide. At this stage, the specialized animals disappear entirely. What remains is an altered patch of seafloor, one with carbonate deposits, layers of shells, persistent mineral structures, and chemical signatures etched into the sediment. These remnants show that life once anchored itself here, relying on steady flows from beneath the Earth's crust. The ghost of the community stays embedded in the geological record, waiting for researchers to uncover the story of how it formed, thrived, and eventually declined. The life and death of a seep demonstrate how deeply ecosystems depend on steady energy sources. In surface environments, rapid changes occur as storms, seasons, and migrations shift conditions. In the deep ocean, where conditions remain mostly constant, the primary force driving biological cycles lies in the presence or absence of chemical flow. When the river runs dry, the community adjusts at a pace matching the geological processes that created it. No panic sweeps through the system. Instead, there is a slow unwinding, a gradual diminishment that mirrors the slow build-up that occurred generations earlier. The long-term nature of this process reveals an important aspect of deep-sea ecology. Stability and change coexist over centuries. A seep may flourish long enough for multiple generations of tube worms, mussels, and clams to grow and die. Then, over decades, the same community may decline as the chemical flow weakens. This slow rhythm contrasts with the more rapid cycles familiar from surface ecosystems, but the pattern remains a cycle nevertheless, a rise, a peak, and a tapering that shape the seafloor across geological timescales. Even after its decline, a seep's legacy influences future ecosystems. If a new seep opens nearby, larvae drifting through the area may settle on the old carbonate structures or shells, using them as foundations for new growth. The remnants of one seep may support the beginning of another, linking generations of communities through layers of geological memory. The new seep may establish itself in a slightly different location, due to shifting sediment or evolving cracks in the Earth's crust. but it often inherits the remnants of the older structure. This continuity shows how seep ecosystems evolve not in isolation, but through repeated cycles of activity woven into the larger fabric of the ocean floor. In this way, the story of a seep does not end when the flow stops. The chemical traces remain, the structures persist, and the memory of the community becomes part of the seafloor itself. Future organisms, future seeps, and future researchers rely on these remnants to understand how life unfolds in the deep. The end of a seep marks a transition rather than a disappearance, one chapter in the long, quiet exchange between geological forces and biological adaptation that defines life where the Earth releases its cold, steady rivers from beneath the surface. In any discussion of Earth's earliest life, attention often turns to the environments where energy was reliably available, long before sunlight became a widespread source. The deep ocean, with its chemical gradients and steady geological processes, offers clues about how the first organisms might have gathered, persisted, and evolved billions of years ago. Although modern cold seeps differ in many ways from the primordial settings that shaped early life, their fundamental principles echo those ancient conditions. They demonstrate how ecosystems can form without sunlight, how microbes can harness chemical reactions to sustain themselves, and how biological systems can organize around steady but unconventional energy sources. By examining cold seeps, researchers gain insight into what the earliest ecosystems may have looked like, and how life survived on a young Earth dominated by chemical rather than solar energy. The earliest forms of life likely emerged in environments where chemical reactions provided accessible energy. On the early Earth, the atmosphere lacked oxygen, ultraviolet radiation reached the surface with little filtering, and conditions fluctuated wildly. Life needed stability somewhere, places where essential reactions could occur reliably. Geological processes deep beneath the ocean provided that stability. Fluids rich in hydrogen, methane, sulfide, and other reduced compounds seeped through cracks and into the overlying water. These fluids met seawater containing oxidized components such as sulfate or carbon dioxide. The resulting chemical gradients formed natural reactors capable of supporting metabolic pathways. In many ways, this resembles what occurs at modern cold seeps, albeit under different conditions and with much simpler life forms in the distant past. Microbes at modern seeps harness energy through reactions that mirror some of the metabolic strategies hypothesized for early life. They oxidize hydrogen, sulfide, methane, and hydrogen, using enzymes that require no sunlight and little oxygen. These reactions generate energy by transferring electrons from reduced compounds to available acceptors. On the early Earth, similar processes likely drove the first metabolic pathways. Before photosynthesis developed, chemical energy would have formed the foundation for all biological activity. Cold seeps illustrate how such pathways remain functional today, showing that these processes are not only viable, but capable of supporting complex ecosystems when conditions remain stable. One of the strongest connections between cold seeps and early life lies in the role of minerals. At modern seeps, carbonate forms through microbial activity, creating stable structures that persist long after the seep declines. In ancient oceans, minerals such as iron sulfide may have played similar roles. Some hypotheses propose that early life began within mineral pores where chemical gradients enabled repeated reactions. These mineral structures could have provided the first compartments, primitive analogues to cellular membranes, allowing reactions to concentrate and organize. Cold seeps today show how mineral surfaces still act as scaffolds for microbial growth and chemical exchange. The mineralized carbonates, although different in composition, serve as reminders that geological structures and biological processes have been intertwined from the start. Examining the slow, steady chemical environment of a seep helps illuminate how early life persisted through challenges. Before oxygen accumulated in the atmosphere, organisms had to tolerate or use compounds that most modern animals avoid. Hydrogen sulfide and methane were common, and the ability to metabolize them provided significant advantages. Microbes capable of exploiting these molecules could colonize environments where chemical flow remained consistent, much as they do today at cold seeps. Their metabolic strategies served as precursors to more complex pathways that evolved later. The efficiency with which seep microbes convert reduced compounds into energy reflects the persistence of ancient biochemistry across billions of years. Cold seeps also reveal how early ecosystems may have developed structure. When the first microbial mats formed on the ocean floor, they altered the environment just as modern mats alter seep zones. They created layers where different metabolic strategies operated at various depths. For example, hydrogen sulfide oxidizers might dominate the surface where oxidants remained available, while anaerobic microbes would thrive beneath them, shielded from oxygen and using entirely different pathways. This layered organization allowed early ecosystems to maximize energy extraction from limited resources. Today's seep communities retain similar layering, with different microbes occupying distinct positions based on chemical availability. The resemblance suggests that cold seeps serve as modern analogues to ancient microbial landscapes. As early ecosystems developed greater complexity, interactions between different microbial groups shaped how energy flowed through the environment. The process where anaerobic microbes oxidize methane while reducing sulfate represents a cooperative reaction that depends on the presence of multiple species. Such metabolic cooperation likely played a major role in early life's expansion. Chemical gradients offered opportunities for specialization, and once specialization occurred, microbes developed interconnected systems resembling primitive food webs. Cold seeps show how these interdependencies remain essential even in modern microbial communities. The reactions performed by one group create conditions necessary for another, forming loops that maintain stability. Considering the role of oxygen also helps connect cold seeps to early life. For most of Earth's history, oxygen was scarce. In such environments, metabolic pathways had to operate without it. Cold seeps demonstrate how life continues to function without oxygen today, showing that anaerobic metabolism remains a viable and efficient strategy. The microbes in seep sediments rely on sulfate, nitrate, or other oxidized compounds rather than oxygen. These pathways existed long before oxygen became abundant and remain important in places where oxygen never penetrates. Their persistence provides evidence for how deeply these early mechanisms are embedded in life's history. The animals that partner with microbes at seeps also provide useful insight, not because such relationships existed in early life, but because they show how far chemical-based ecosystems can develop. Life in early oceans lacked complex organisms, yet the principles remain consistent. Microbes act as primary producers, converting chemical energy into usable forms. Other organisms evolved to take advantage of this microbial activity. The appearance of tube worms, mussels, and clams in modern seeps reveals that chemical ecosystems can support large, multicellular life once conditions become favourable. While such complexity took billions of years to arise, the underlying structure, microbes capturing energy and other organisms relying on them, likely dates back to the earlier stages of life on Earth. Cold seeps also provide clues about how life might have spread across the early ocean. Before photosynthesis became widespread, ecosystems had to form wherever chemical energy remained available. As the planet's crust shifted and new cracks opened, chemical-rich fluids seeped into the water. Microbes colonized these areas, leaving chemical and mineral traces behind. When seep flow diminished, the microbial communities either died or entered dormant states, much as they do today. New communities formed when new seepage emerged. Over long timescales, these shifting habitats created a patchwork of chemically driven ecosystems across the ocean floor. Modern cold seeps, with their cycles of growth and decline, mirror this dynamic pattern, offering insight into how early life might have migrated or expanded gradually in response to geological changes. Studying these environments also addresses broader questions about the conditions necessary for life. If ecosystems can form around chemical flows deep underwater, far removed from sunlight, then the essential ingredients for life narrow to energy, water, and a source of reduced and oxidized compounds. Early Earth had all of these. Modern seeps show that life does not require a wide range of nutrients or constant environmental change. Stability, even if defined by slow chemical reactions, can support growth and diversification. The predictability of seep chemistry makes it easy to imagine early organisms finding footholds in environments that remained stable for long periods. The role of methane in particular provides a link between modern seeps and early life. Methane was far more abundant on the early Earth, both biologically produced and geologically released. Microbes capable of oxidizing methane would have had access to a widespread energy source. Today's methane-oxidizing microbes represent descendants of these ancient organisms, carrying metabolic pathways that originated before complex life appeared. Their presence at cold seeps demonstrates the long continuity of methane-based metabolism in Earth's history. Hydrogen, too, offers another connection. Some seep microbes use hydrogen as an energy source, a pathway considered one of the oldest forms of metabolism. Hydrogen was plentiful on the early Earth, and reactions involving hydrogen and carbon dioxide may have driven early biochemical processes. Cold seeps show how hydrogen can still fuel entire microbial communities in modern oceans. These parallels strengthen the idea that cold seeps reflect conditions not just similar to early Earth, but potentially essential to the origin of life. The geological setting of cold seeps further illustrates how early environments may have combined stability with slow change. The seep's chemical output can last centuries or millennia, providing long time frames for biological adaptation. On the early Earth, chemical gradients likely persisted for similar durations as geological formation shifted slowly. Microbes that developed efficient strategies for extracting energy from these gradients could have persisted long enough to explore new metabolic possibilities. The gradual nature of seep evolution parallels the slow pace of biological innovation in early life, emphasizing the alignment between environmental timescales and evolutionary ones. Modern seep communities, with their structured layers and interdependent species, offer a glimpse into how simple associations may have scaled upward over time. A single microbial layer may have expanded into multiple layers with different metabolic roles. Cooperative relationships may have formed where one group depended on the byproducts of another. These patterns occur at seeps today, suggesting that early life may have followed similar trajectories. Complexity builds not through sudden leaps, but through incremental changes that accumulate as long as energy remains available. Even the decline of a seep provides insight into early life's resilience. When chemical flows fade, microbes adjust by slowing their metabolism or entering dormant states. Some survive within deeper sediment layers, others disperse through currents or move with shifting sediment. This resilience mirrors what early life needed to survive geological fluctuations. Energy sources did not remain constant, and early life had to tolerate periods of scarcity. Cold seeps show how modern microbes manage such transitions, shedding light on how early organisms might have navigated similar challenges. All of these connections highlight why researchers often point to environments like cold seeps when discussing the origins of life. They demonstrate how ecosystems can begin without sunlight, how metabolism can adapt to available chemical energy, and how geological processes shape biological evolution. They show that life thrives when energy flows consistently, regardless of the form that energy takes. They reveal how cooperation between microbes emerges naturally when chemical gradients overlap. They illustrate the layered complexity that can form around simple reactions. Cold seeps are not direct replicas of early Earth, but they preserve essential principles that characterized Earth's first ecosystems. They help explain how life may have taken its early steps, how it shaped its environment, and how it persisted long enough to evolve into more complex forms. By studying these deep, quiet environments, scientists reconstruct a picture of a world where life began not in sunlight, but in chemical shadows. where energy seeped upward from the Earth's interior, and microbes learned to turn those flows into the first sustained breaths of biology. In the deep regions where cold seeps send their slow chemical flows into the surrounding water, the story they tell is not limited to biology, geology, or the long arc of Earth's history. It becomes clearer only when stepping back and looking at everything together. The structures built by tube worms and mussels, the microbial transformations happening in the sediment, the predators and wanderers weaving in and out, and the cycles of growth and decline that shape the seafloor over centuries. By the time all of these pieces fit into place, the seeps begin to reveal something broader. They show how life develops around opportunity rather than familiarity, how ecosystems anchor themselves to whatever energy source remains consistent, and how subtle processes accumulate to form entire worlds hidden beneath darkness and pressure. Moving upward from the details of the seep, the broader lessons come into focus slowly, shaped by the same steady rhythm that defines the environment itself. One of the clearest lessons lies in how life adapts to energy sources outside the familiar pathways powered by sunlight. At the surface, photosynthesis dominates almost every food chain, and biological diversity responds to cycles of light and day. It becomes easy to assume that life depends on the presence of sunlight, or at least on conditions that trace back to it. Cold seeps contradict this assumption entirely. They show that life flourishes where chemical reactions, not light, supply energy. The microbes that oxidize hydrogen sulfide and methane prove that metabolic pathways need no sunlight to function. The animals that depend on these microbes show that complex life can anchor itself to ecosystems where light never reaches. The presence of thriving communities in these environments shifts the definition of habitability. It suggests that energy, not sunlight, forms the fundamental requirement for sustaining life. Wherever consistent energy gradients appear, life has a chance to take hold, whether in the deep ocean beneath ice cover or even on other planets if similar conditions exist. The second lesson emerges from the interplay between geological processes and biological growth. Cold seeps exist because of the way Earth moves fluids through its crust, pushing methane and hydrogen sulfide upward over long periods. These geological actions shape the availability of resources, the location of communities, and the lifespan of ecosystems. Biology responds by settling where chemical flow occurs, altering sediment structure, forming carbonate deposits, and building multi-layered habitats around the seep. Over decades and centuries, the combined impact of biological growth and geological processes reshapes the seafloor. Tube worms build upward, mussels spread outward, and microbes strengthen carbonate foundations beneath them. The result is a merged system where geology and biology cannot be separated cleanly. Cold seeps demonstrate that life does not simply occupy the environments it finds, it modifies them, reinforcing chemical pathways, stabilizing substrates, and leaving behind geological signatures that persist long after the community fades. This interplay reveals how geology and biology co-evolve, influencing one another through long-term processes that quietly reshape the planet. Another lesson comes from the persistence and resilience of life in an environment that offers stability without abundance. Cold seeps do not provide rapid surges of energy. They offer steady, modest chemical flow that persists for decades or centuries. The organisms living there grow slowly, reproduce at measured rates, and maintain equilibrium through cautious biochemical balance. Their survival does not depend on speed or competition in the way many surface species rely on rapid responses to changing seasons. Instead, seep organisms demonstrate a different form of resilience, one rooted in long-term stability, efficient symbiosis, and fine-tuned adaptations. Their pace mirrors the slow, geological pulse beneath them. They show that ecosystems need not be fast or crowded to be successful. They can thrive under conditions where patience and biochemical precision matter more than rapid change. Cold seeps also reveal that complexity does not require abundance. The deep ocean receives little organic material from the surface, and in most places life remains sparse. Yet where seep fluids emerge, complexity flourishes. Microbes create the base of the food web. Tube worms, mussels, and clams form layered structures. Predators move between these layers. Wanderers and transient species drift through, contributing additional interactions. These communities show how energy can focus biological activity into concentrated zones, even in vast regions of relative emptiness. The seep serve as reminders that ecosystems can flourish around narrow, localized opportunities. They teach that biological richness does not always arise from widespread resources. Sometimes it centers around specific points where conditions allow life to gather densely. Another insight emerges when considering how these communities change over time. A seep begins quietly, develops into a structured habitat, supports thousands of organisms, and then eventually diminishes as geological forces shift. The decline happens gradually, reflecting the methodical pace of the deep ocean. Tube worms thin out, mussel beds shrink, microbial mats fade, and predators search elsewhere. Yet the community does not collapse suddenly. Instead, it transitions slowly into a state where only remnants remain. This long-term pattern demonstrates how ecosystems can rise, flourish, and decline without abrupt disruption. It offers a model of ecological time that differs from rapid cycles seen in surface environments. The seep's lifespan teaches that environmental change need not be dramatic to shape life. Small, persistent shifts accumulate into large-scale transformations, influencing both biological communities and the geological structures beneath them. The remnants left behind after a seep declines show how ecosystems leave marks that persist long after they disappear. Carbonate structures, layers of shells, and faint traces of chemical activity remain embedded in the sediment. These remnants allow scientists to study seeps long after their energy sources fade. But beyond scientific insight, these remnants demonstrate a larger principle. Life alters its environment in lasting ways. Even after organisms die or disperse, their influence lingers. Cold seeps show how biological activity becomes part of the geological record, documenting the presence of communities that shaped their surroundings through quiet, persistent interactions. The seafloor becomes a layered archive, preserving evidence of a life's imprint across generations. Examining cold seeps also provides perspective on the connection between modern ecosystems and Earth's ancient past. The metabolic processes driving seep communities resemble some of the oldest biochemical pathways on the planet. Long before photosynthesis evolved, early microbes likely relied on similar chemical reactions to extract energy from their surroundings. The layered microbial mats, the chemical gradients, and the mineral deposits produced by seep microbes reflect patterns that may have characterized early Earth. This connection does not mean cold seeps recreate those ancient environments perfectly, but they offer glimpses into how life might have persisted before oxygen became widespread. They allow modern studies to bridge billions of years of evolution by observing metabolic strategies that have endured across Earth's history. Cold seeps teach that life's foundation remains flexible enough to operate under conditions vastly different from those familiar today. Another lesson arises from observing how organisms collaborate in these ecosystems. The symbiotic relationships between animals and microbes reveal that survival often hinges on cooperation rather than independence. Tube worms cannot survive without their bacterial symbionts. Mussels and clams rely on internal microbial communities to process chemical compounds. Microbes depend on their hosts for controlled environments that supply sulfide, methane, oxygen, or sulfate at levels needed for metabolism. This interdependence shows that ecosystems thrive when different organisms combine their strengths. Instead of competing for limited resources, they integrate their functions to unlock energy sources no organism could exploit alone. These cooperative systems highlight how complexity grows through partnerships. The presence of predators, scavengers, and wanderers adds another dimension, showing that ecosystems built around chemical energy still connect to broader networks of life. The seep does not exist in isolation, even though its core species remain specialized. The occasional visitors demonstrate that no environment stands completely separate from others. Life moves, explores, and adapts across boundaries. Cold seeps teach that ecosystems are shaped not only by internal dynamics, but also by external interactions that occur unpredictably. These connections help maintain ecological diversity through subtle exchanges between species and environments. On a larger scale, cold seeps illustrate how life adapts to constraints. The deep ocean imposes pressure, darkness, and limited mobility. Yet organisms find ways to exist comfortably under these conditions. The chemical environment imposes toxicity and low oxygen, yet microbes and animals turn those challenges into opportunities. The geological setting offers slow, steady energy rather than rapid surges, and life adjusts its growth, reproduction, and structure accordingly. Cold seeps serve as examples of how constraints do not limit life's possibilities. Instead, they shape pathways for adaptation, guiding the evolution of traits that match the environment's steady rhythm. The teachings of cold seeps become even clearer when considering how they expand the sense of where life can exist. They show that environments once assumed to be uninhabitable are not only habitable, but capable of supporting intricate long-lived ecosystems. They challenge assumptions about what life requires. They broaden the criteria for searching for life on other worlds. They provide analogues for environments beneath the icy crusts of moons like Europa or Enceladus, where chemical gradients may fuel microbial communities beneath global oceans. Cold seeps teach that life's requirements are not universal. They are contextual, shaped by the energy available. At their core, these hidden rivers teach patience, persistence, and balance. They demonstrate how ecosystems evolve gradually through interactions among microbes, animals, and the geological forces beneath them. They show how energy shapes structure, how cooperation generates stability, and how life leaves enduring marks even in environments that seem detached from the world above. They remind us that life adapts not by resisting what exists, but by integrating with it, finding ways to turn challenging conditions into sources of strength. As the narrative moves back upward from the depths, the seeps leave behind a sense of quiet complexity. They reveal that beneath the calm exterior of the deep ocean lies a system shaped by subtle processes, chemical flows rising from the Earth's interior, microbes converting those flows into energy, animals building structures around them, and entire communities adjusting to slow changes over centuries. The hidden rivers of the deep show that life's story is not just about abundance and speed, but also about endurance, adaptation, and the ability to thrive in places shaped by steady, unseen forces. They teach that every environment holds potential, and that life, given time and opportunity, can find ways to grow even in the most unlikely corners of the world.